When you study fluid kinematics, you are mapping the geometry of motion, velocity, and acceleration without asking what causes the fluid to move. Fluid dynamics answers that question. Here, we analyze the active physical forces and the energy driving the flow. The governing physics behind this is Newton's second law: pressure, viscous friction, compressibility, and surface tension. Not all of these forces carry the same weight in every scenario. For standard macroscopic pipe flow, gravity and pressure are the core driving forces that survive our initial mathematical filtering. Because of this, the mass of the fluid and the specific forces acting upon it become the primary inputs you will use for your engineering calculations. Engineers simplify complex real-world flow by dropping negligible forces. First, assuming zero compressibility and surface tension takes us from Newton's second law down to the Reynolds equation. Next, assuming laminar flow lets us drop the turbulence force, leaving the Navier-Stokes equation. Here is a high-yield shortcut for your AEE exams. Assuming an ideal, non-viscous fluid lets you eliminate viscous and shear stress forces. That leaves only gravity and pressure, bringing you directly to Euler's equation. This is Euler's differential equation of motion. Along a single streamline, changes in pressure, gravity, and velocity sum to zero. You must memorize the 4 strict assumptions to arrive here. The fluid must be ideal, steady, incompressible, and one-dimensional. In a steady, ideal flow, the total energy of a fluid remains perfectly constant from one point to another. This equation is Bernoulli's principle, representing the direct mathematical translation of that energy conservation principle. The formula breaks down into 3 physical manifestations of energy: kinetic energy derived from velocity, flow work energy derived from pressure, and potential energy derived from elevation. Because the total energy is constant, we can create a measurement mechanism. If we intentionally force the fluid's velocity to change by altering the pipe, the pressure must universally react in the opposite direction to compensate. This pressure reaction acts as our diagnostic signal, which we can read as a physical height difference in a static column of fluid. This diagram shows a differential manometer bridging the gap. By connecting an inverted U-tube across 2 points, we can safely read this internal pressure differential from the outside. Extracting this pressure reading provides the exact variable needed to reverse engineer the fluid's actual velocity and calculate the total discharge volume. There is a critical caveat to this math. Bernoulli's equation assumes a frictionless ideal fluid, which does not exist in the real world. Real fluids experience internal friction, and their momentum causes them to physically separate from the pipe walls when their velocity is suddenly manipulated by physical devices. To measure real-world flow, we bridge theoretical physics and empirical reality using device-specific geometric designs and mathematical coefficients. Engineers prioritize the venturimeter for high-pressure systems because it measures total flow while preserving nearly all the fluid's initial energy. This cross-section presents the 3 physical zones of the device: a converging cone, a narrow throat, and a diverging cone. During the acceleration phase, the gradual convergence forces the fluid to speed up, dropping the fluid's pressure to its lowest point exactly at the throat. This exact pressure drop is measured by the attached U-tube manometer, providing our key H variable. Notice the asymmetry of the device. It has a steep, sudden entry angle, but a much shallower, elongated exit angle. This geometry addresses flow separation. When fluid is forced to expand too quickly, its forward momentum causes it to detach completely from the expanding pipe walls. In theoretical models, an ideal fluid behaves perfectly, smoothly following a gently expanding surface without detaching from the pipe walls or losing any internal energy. This design note specifies that the diverging angle is strictly constrained to between 5 and 7 degrees. This shallow angle gently guides the fluid back to pipe width, specifically preventing detachment and avoiding permanent head loss. This geometric elegance translates mathematically. The actual physical discharge remains remarkably close to the theoretical discharge derived from Bernoulli's equation. By investing in a larger physical footprint to prevent flow separation, the venturimeter achieves a high coefficient of discharge, reliably hitting between 0.95 and 0.98. The orifice meter provides a space-saving but physically violent alternative. This diagram outlines its simple mechanism: a sudden restriction plate placed directly into the path of the flowing fluid. Because of inertia, the rapid fluid cannot instantly make a 90-degree turn through the small hole. This creates the vena contracta. Due to inward momentum, the narrowest fluid jet occurs slightly downstream of the plate, rather than inside it. This violent, sudden contraction is followed immediately by an unguided expansion back to full pipe width. Without a gently angled cone to guide the expansion, massive flow separation occurs, creating chaotic, energy-destroying eddies in the dead zones directly behind the plate. This permanent head loss slashes the mathematical efficiency. The device's coefficient of discharge drops heavily to between 0.61 and 0.65. The orange box clarifies the area variable, A0. In calculation, this represents the diameter of the physical orifice plate itself, rather than the slightly smaller diameter of the vena contracta jet. The orifice meter proves that cheaper physical designs exact a heavy mathematical penalty, trading efficiency for economy. Instead of measuring the total volume of fluid moving through the entire pipe, we sometimes need to measure velocity at one single precise point. This requirement introduces the pitot tube, a device that operates on a completely different physical interaction than area constriction. This diagram shows the mechanism, an L-shaped tube facing directly into the oncoming fluid flow. The exact tip of the tube is the stagnation point, where a single fluid streamline is brought to a dead stop. Because velocity drops to absolute zero, 100% of its kinetic energy instantly converts into pressure energy. Walking through the Bernoulli derivation, since the velocity at point 2 equals 0, that dynamic pressure head is perfectly isolated in the equation. This final velocity formula utilizes the coefficient of velocity, or CV, to account for the minor frictional losses that occur right at the tube's tip. By utilizing stagnation, the pitot tube offers an elegant, minimal loss method to map the exact velocity profile across any cross-section of a pipe. Understanding theoretical device geometry is only half the battle. In competitive environments, you have to execute the math under pressure without compromising technical precision. This past paper problem requires the calculation of actual discharge using provided pipe areas and a manometer reading. Step 1 sets up the standard Venturi discharge formula to process these variables. The primary failure point in this setup is a lack of unit consistency across the entire equation. Specifically, if the area inputs are provided in square centimeters, the gravity constant cannot be the standard 9.81 meters per second squared. As noted in Step 2, gravity must be converted to CGS units, utilizing 981 centimeters per second squared to match the area inputs. Executing the mechanics of the formula, Step 3 shows how the denominator simplifies beautifully to a whole number. Resolving the final math yields the actual discharge rate, emphasizing that the final unit is strictly cubic centimeters per second. This quick recall sheet highlights the core constants and ideal assumptions that must be properly managed before executing these equations. Predicting fluid behavior requires visualizing the physical geometry of flow separation. Understanding these mechanics makes the formulas a logical necessity rather than a memorized sequence.